So first of all, I would like to talk, to thank July for the invitation to talk in this seminar, and to Frederick also, to Andre, and to Serge, and to CRM for making possible our long visit for me and my family. So thank you. And I also want to say that in 2017, I visited Montreal to go to the Mathematical Congress of the Americas. At the time, Frederick invited me to give a talk here at camp. So I talk about the first part of this project. It was Rowlett, about the determinant on sectors. And of course, not all of you were here, and I don't expect the ones who were here to remember. So I will just go from the beginning. But this is like continuation of that project of which I talked here before. Okay, so I will first start with some motivation and basic definitions, and then I will give the formulas, the results that we have about these things. M and G. This is a compact Riemannian manifold. Dimension n, and then later I specify to dimension 2. More general. So M is a manifold whose chars are same. The transition maps are smooth, so we always consider it smooth, unless we say the opposite. And G is the Riemannian metric. Is when one assigns to each point in the tangent space, we have a point, the tangent space, and then we assign an inner product, and this is done in a smooth way. So that's the Riemannian metric, and that Riemannian metric induces a distance and the Vichy-Beta connection, so we can differentiate the whole tensor algebra. Also, use the measure, the two measures, so we can integrate and do everything in the manifold. That's what we do with the Riemannian metric. So, okay, so we have all that, and then we have the Laplace operator. We can have it on functions, the Laplace Beltrami operator, or on forms. The level of functions, the Laplacian, they coincide. So I write it as minus divergence of the gradient and apply it to functions. So this will be this. And in terms of the local coordinates, so I can write the metric like this Gij. The matrix that is positive definite and its inverse. I write like Gij with upper index. Then this is given like in terms of minus the inverse of the metric, and then we have Xi. This is in local coordinates, the function plus lower order terms. So we have that this second order differential operator that is elliptic. So if M is compact, or if M is closed, then we have that this Laplace operator is essentially self-adjoint, so it has a self-adjoint extension from the smooth functions. But otherwise, if it has a boundary, so this is for M compact. So close, for those who don't know, is compact without border. that if it's not closed, but still compact, so if it has a boundary, then it's not essentially self-adjoint, and then one has to choose a self-adjoint extension. And that's one does imposing boundary conditions. So in general, we should always choose the Dirichlet Laplacian, but one can also choose other boundary conditions. Okay. The Dirichlet boundary conditions fix the value of the function on the boundary. So and with this, when one has a self-adjoint operator, one can talk about the spectrum. So we can talk about the spectrum of the Laplace operator. And so on a Riemannian manifold, so the spectrum, or that we look at the eigenvalue equation. We look at solutions of this equation such that U is different from 0. And if we have a boundary, then we will impose that U restricted to the boundary is equal to 0. These are the Dirichlet boundary conditions. So we solve the equation, and then we have the spectrum of the Laplace operator that are manifold. We have is only discrete. So this will consist of a sequence of eigenvalues. And if we have connected, if there is 0 in the spectrum, it's only of multiplicity 1. And then this is a sequence that goes to infinity, and that follows from the fact that the resultant is a compact operator. And so on the spectrum. And then if has a boundary, so 0 is not an eigenvalue. And if has a boundary, have a boundary, then 0 is an eigenvalue because the constant functions are the 0 eigenfunctions. Okay. So that's in general for any compact Riemannian manifold. And now I want to give 2 examples that are very simple. Well, one is simple, the other one is also useful. So the first example is the easiest example. Is we have the closed interval 0, 1. So here, the Laplace operator denoted like this. So it is closed with boundary, and then I mean the interval is closed, so it's compact with boundary. And so we need boundary conditions. So we have boundary conditions. So yeah, we have that the Laplace operator is just taking the 2 derivatives. And so we have the Dirichlet Laplacian that fits the domain. So we have the Dirichlet eigenvalue problem. And then with U 0 equals 0 equals. And then the solutions are UN of, or let's say UJ of X, and then we have sine of N 5 X. And this is for N greater or equal to 1. So the eigenvalues here are, I'm sorry, this is J. I had N in mind, but So it doesn't matter. Okay. This is the answer, the eigenvalues. That's the spectrum is the set of eigenvalues with J greater or equal to 1. And now I have another example. Is the sector. So we have the sector of radius 1 and opening angle alpha in the plane. That's alpha. This is radius 1 alpha. So this is the I. What position R between 0 and 1. And the angle goes between 0 and alpha. So this is contained in R2, and then the metric is the Euclidean metric of R2 restricted to the sector. You have the metric is Euclidean. This is R2, R2. And the LaPlace operator, the same Laplacian, but now in polar coordinates. But it's the Laplacian in polar coordinates. So I just write it like this because we just restrict to a sector. It's the same here. -1 yeah, for R squared. That's the Laplacian, and then one can compute things explicitly, and then one can compute the eigenvalues. Let's tell you what are the eigenvalues. Okay, so the eigenvalues. So we can compute using separation of variables. The eigenvalues are lambda and L squared with n and n equal to 1. And these are so lambda and L is the nth 0. Of well, and here as we have boundary, we have the Dirichlet Laplacian, so the Dirichlet boundary conditions. The n is positive 0 of the Bessel function. Okay, so this is Bessel function of the first kind. J, and this is a phi over order of the Bessel function. So the Bessel function solves the Bessel equation, and then the eigenvalues in this case are going to be that can be computed. Okay, and this is what we have. So L here is bigger than 1, and N is also bigger than 1. So what we want to do next is to define the determinant of the Laplace operator. So we want to define the determinant of the determinant of the function. So when we have a matrix, one usually considers the determinant is the product of the eigenvalues. But what happens if one wants to consider that here? So if we want to consider the product, okay, and for the determinant, we take some regularization a priori, is that if 0 is an eigenvalue, we just take it out, otherwise we have 0. So we consider non-zero eigenvalues, So we have the product of the lambda j different from 0 of lambda j. So we want to have something like that, but that is impossible because, or well, it's possible, but it diverges. That's because here we have a sequence, so an infinite amount of numbers that goes to infinity. So this is going to be divergent. So that's going to be infinity, but as we know, that is never a problem because we can find a regularization. And this will be divergent. So we will make a regularization that is called the zeta regularization. So, and there are other ways of making regularizations of determinants. But we consider this one. And this was introduced by Ray and Singer. So this consists in considering the spectral zeta function. That is function of a complex variable s, so s in the complex plane, and then let me see. I wanted to write it. So this is the standard thing. Consider lambda j different from 0, like lambda j to the minus s. So this is just the trace of the Laplacian minus the projection in the kernel. This is if there is kernel, so the zero space to the trace of this. So this is the spectral zeta function, and this is defined in general for real part of s bigger than n over 2. And so we know several things about the spectrum. In particular, we know how these eigenvalues grow. That's called Bayes' law. I don't write it. It's called Bayes' law. And because of this way in which it grows, we know that this converges, or this half plane. So what is the trick? The trick is to extend this function to the whole plane and have it regular at 0. So I will write something. So this. And this converges. Now the point is that this property that it has a metamorphic extension. Regular. And yes, equals to 0. And with that, we can define, with this metamorphic extension, we can define the determinant of the Laplace operator as exponential of minus derivative is of the spectral zeta function. Sorry, yeah, it's more. So we just write zeta prime at 0, but according to the metamorphic extension that we use. And this extends, if we want to make the computation formally, we will see that it just extends this of a growth, but in it will converge. It will be real. And a number. Positive. So
That's the definition of determinant.
yes, this is the definition of that. Some question? I think that.
Is there another way of using functional analysis to find the determinant?
Yes, there are all ways of defining determinants, and actually that's an area of study of defining different determinants of different algebras of operators. I usually use this determinant. So there are other determinants that we define, but it's all. Yeah. I mean, this is the determinant in this case. When one cannot define the determinant, they have maybe I say something at the end. So here is an example. I can't remember in this area, so an example. Because I give this example because it's very easy. Is if we have again the interval. And then we have the spectral zeta function for this interval. This is, so we have here the sum, and then I will write here the. Here we have 5 and no. So this is just two minus it. So this is the sum of infinity, and here we have the minus 2s and the minus 2s, and then this just 2s. And here, I don't know if you recognize, this is the Riemann zeta function. Riemann zeta function of 2s. And then one can differentiate this expression. And one knows that this Riemann zeta function has also some extension, and we know we can compute the values. So we have that the derivative of 0, so the extension is already minus 2 log of 5. Then we have the R of 0 as 2 time of 0, and this value is minus 1/2, and this value is minus log of 2 pi. So we will have that with these values, we will have like this here, minus 1/2, and this is of square root of 2 pi. Yeah. And with that, we have the determinant of this operator here is plus 2. So that gives us a number. But to do these computations, it's not so easy, because one has to compute the spectrum, and then one has to hope be able to write the spectral zeta function in terms of some function whose extension we know and whose values could be computed explicitly. So it's really not so easy in general. Okay. So okay, so now I should say a few things about determinants, why to study determinants, and so motivation. More like a advertisement for determinant. So the first is that on this process of the determinant gives us a global invariant. So this is a number that depends on the spectrum and is not local. One cannot write it in terms of local quantities. So that's about the determinant. And this is not restricted to the Laplace operator. We can do it for any differential operator and also pseudo differential operators. But okay, for the determinant of the Laplacian, we have it with a global invariant. So to a metric, we just have the determinant of this. So it can help maybe to study spaces of metrics. And what is interesting is that its variation. So itself is not local, but its variation is local. So one can compute many things. Yes. The second reason why it's important for me is that one uses the determinants of Laplacians to define analytic torsion. So one defines analytic torsion using the determinant of the hot Laplacian in all layers of forms. And this analytic torsion equals Riemann master torsion that is a topological invariant. And so this was proved by Ziegler and Müller separately. And there are some generalization to other settings by Frederick and here. And I think I'm missing somebody else. I don't know. You know Frederick? Generalization. I know he was had done this, and for in geometry is a potential for the White-Peterson metric. So in hyperbolic surfaces. The Euler space. And in addition, it's related to Liouville actions in quantum field theories. And also the Casimir effect is related to certain values of the spectral interaction. So this is just some reasons. I will not extend myself more on that. So that's why it's interesting for me. It's interesting because it's also a quantity that is in it relates geometry with analysis, with mathematical physics, also with number theory. So it's really a very interesting quantity to study. So okay, so now let me tell you how this metamorphic extension is obtained. But that's one need quickly. So for the metamorphic extension, there are also some ways of doing it. That's the one we use. So one can use either have the trace of the resolvent, but one can also use the trace of the heat operator. That's the one that one uses. So one has we use the trace. But as I said, it's not the only method. Heat operator. One can construct a heat operator associated to this Laplace operator. So it has to do with the equation, the solutions of the equation. One can also use it using the spectral theorem. And so we have this heat operator, and on a compact manifold, this is space class. And its trace is just the heat trace given like this minus T lambda J in the spectrum. And how does this relate? Is because one can write the spectral zeta function. So using Mellin transform, we have this expression involving the exponentials of the eigenvalues. So using this, I can write this like this integral, and here I have phase of little minus T G, and here I take the projection in the kernel of delta G, and then here T is minus 1 dt. So this is using Mellin transform. That's Mellin transform the other expression, and I obtain this. Here I take the projection because it already here. And so this is an integral operator. But it is an integral operator says that I can obtain the I can apply it through an integral curve. So minus the acting on a function. This will be just the integral over the manifold of the integral kernel, that's the heat kernel, which is T and F of So, and then this is the integral kernel, this is the heat kernel. And what is important is that the trace and the kernel, in this case, have an asymptotic expansion as t goes to 0, because as t goes to 0, this goes to 1, and then all this diverges. So we can have an asymptotic expansion for this divergent trace and see how it diverges depending on t. And the same happens for the kernel. So, go down to 0. So, this is the trace of theta minus t delta. So this expansion is theta minus n over 2. Then we have the sum of 0 to infinity aj. And for the heat kernel, we have the corresponding one. Well, this I usually don't write. Okay. Oh, here we have some functions. In general, so these numbers that appear here are also spectral invariants, and they are called heat invariants, and then they have information about the geometry of the manifold. And I will not comment much on that. I just write it because I will explain something about it later. So what one does for this extension is that one uses this expansion here for the interval between 0 and some fixed number, and then one can extend the zeta function in that way. I think that we will have the metamorphic extension there. So I want to mention another motivation. Is that Felix and Sarnak proved this in 88. So they had two papers with determinants. One was about extremals of the determinants on surfaces, and another was about compactness of spectral surfaces. So I just mentioned this. If we have M, in this case, I just mentioned a closed surface. And then we consider the determinant as function of the state of metric mode with homomorphisms to the real numbers. And then, so the theorem is that if one fixes metrics with an area in a conformal class, the determinant is maximized at the metric of constant scalar curvature in that conformal class. So conformal metrics are I multiply the metric at each point by a positive quantity. Generally, that's why I did this, and then this. This is the conformal factor that you can. So for this kind of metrics, we have that determinant. And then this is the metric of constant scalar curvature in the class. It's bigger than the determinant of each. So this is okay. I always try to find the best way to say no. Oh, 1G. But there's the unique metric, so maybe I can find it and T of constant scalar curvature. So this is like the motivation. And for this, they use Polyakov formula. And I tell you now about Polyakov formula, because that's where I want to go. Oh. So it's actually Polyakov's Alvarez formula. Polyakov and Alvarez. So this formula was introduced by Polyakov, and this without boundary, this with boundary. Correct me if I say something wrong. In relation to quantization of strings. So he was working with quantizing strings, and then he introduced this Polyakov formula because the determinant is related to the action of a string. So for smooth spaces without boundary, I wrote it without boundary first. We have a conformal transformation of the metric. So I have fixed Riemannian metric, a conformal transformation of it. And for this, I will assume that they have what I want. No, I want yes, I want with boundary. Without boundary, I want it with boundary. And we have they have the same area. We consider the area with H. Sorry. And
I'm sorry, maybe there is something I miss. When you write H equal e to the, you don't mean e to the I phi, you mean e to the 2 phi? Is it, I don't listen, I can't read your block.
I'm sorry, you cannot read.
Yes, what
Yeah.
do you mean?
E to 5. And 5 is a function
It's
that
2
is
times, okay, okay.
5, yes. And 5 is always, I didn't say, it's always a smooth function on M. And so what this formula tells me is how they differ, the logarithms of the determinant. So it means how these things are.
So that's an hypothesis.
Yes, this is
That's
a
right.
hypothesis here. Log of the determinant minus log. So how these things differ. So what they call it, how is the anomaly. And so this is equal to. So what is interesting is that these are two global quantities, but this difference is given in terms of only local quantities. So this is -1/12, and here we have the integral over M, and here we have the norm of the normal square of the gradient. And so this would be like the energy function. Here we have our this number. Let me check. But I know. 5. And here I have another integral, and this integral has the scalar curvature, or 12. I always get with the constant. Yes. So I have here a scalar curvature of G multiplied by the function integrated with respect to the background metric V. Here I have -1/6 pi. So I have these two terms related to the interior of the manifold, and I will have two terms related to the boundary of the manifold. So here I have that. Where's the boundary? And here this is the geodesic curvature of the boundary and the conformal factor. And here we have 1/4 pi integral. And here I have the exterior, the exterior derivative, but in the inverse direction of the function is of the function integrated on the boundary of the manifold. So we have this distance. So this is the Polyakov Alvarez formula. Okay. So as I said, this came in relation to quantum quantization of the spin, and it's also used in quantum cosmology. So now I don't know how much time I have. I still have time. So now we want to extend these to surfaces with conical singularities. So for a surface with conical singularities, so we consider the case when we can have, so it's a surface that is everywhere smooth, but in the points of the conical singularities, and we can also have a boundary. Like have some conical singularities. We can have boundary components, we have some other singularity. So there are conical singularities. So they appear here in the interior. So and here we have this point at which singularities appear. So Well, so I describe, so we have here this M, it's a compact manifold. And here we have certain points. There are the points where the singularities are going to be the conical singularities, and we have M is just the interior of this manifold. So this is manifold without the boundary and without the point. So this is M of E union boundary of M. So the difference is that the boundary of M and not just normal M includes the points and the boundary of M is only the boundary component. Okay, so the boundary component of M. So what we have is that the metric G is going to be smooth on M, so on the interior, and well, the boundary that's an usual boundary, and for each conical singularities, the metric is the one of a cone that is a generalized conical singularity. So it's a generalized cone, right? So for each of these, there exists a neighborhood of this point. And we have some epsilon 5 such that this neighborhood is has this form cross, and here we have S1, and then we have that symmetric restricted to this neighborhood is R2 plus R2, and here we have a family of metrics on S1. Smooth one, and so PI is the conical singularity, and the angle here, and the angle is defined as the integral or S1, and here we have this family. This is a metric on S1 at each level of R, and included 0. So this is just, we just integrate here is so the volume of S1 with this metric at 0. Okay, this is the definition of angle, and we restrict the cases where these angles are between 0 and 2 pi. And so for these metrics on the so to each cone there, I will not go over there. So we have a generalized. If this is just the usual metric of on S, we have to say how it is the disk. I will give the example of the cone if I have time. So the Laplace operator here, so we need to consider the Dirichlet Laplacian, because we have boundaries. So Dirichlet from the boundaries, but also we need to take the Friedrichs extension because we have conical conical singularities. So this is the Laplacian that we have in this case. And for this, we know that the spectrum of this LaPlace operator is discrete and has like so. And this, of course, it depends on how we consider the conical singularities and which particularities we have in each case. But I give you the trace of the heat operator and the trace of the heat operator, and this trace has an asymptotic expansion, as in that case, that has also worked out by several people. So I give you this is the formula for in general. So in dimension, we will have that trace of the heat operator here as an asymptotic expansion. Like this will be A0 theta minus 1 and A1 to 1/2. And in general, there appears here a log of t term that is bad for defining the determinant. One. And here we have a peak O of t to the 1/2. This is 1/2. And this is as t goes down to 0. But locally, for dimension two, this term vanishes. So what this term is equal to 0. The dimension is equal to 2. So I give you some names here. Tuning and Sealy. 87. Figure. It is not organized chronologically. And Morse. 99 and King 97. So actually the one who proved this part was King. And yes, and I think there have been others working in these asymptotic expansions. Sorry if I don't mention them. But so as I said, many people have worked on these things. So what we have here is that metamorphically for n equals 2. And then the determinant is what. So I have the determinant of the Laplace operator. And so there are several questions that from here, for example, we can ask, we will have such a theorem like this in this setting. And it's not clear, but apparently it's not, because what about extremal problems? So there are several things. So first of all, one of the problems that can appear is in a conformal class exists metrics of constant curvature. So we know that that is already a restriction because it has to have some conditions, and where there will be constant curvature metrics, will there be a maximum or not? So I want to mention this result by Victor Calvin. It's very well. And that he worked for spheres, and what he proved is he has, I think he's connected. I don't know if it's connected. I saw he was connected, but of course he knows everything I have said now. With two conical singularities. So he has restricts to metrics of constant scalar curvature and area, fixed area for phi. And what he proves is that the determinant is unbounded for this set of metrics. So we will have something like this. And we have that is unbounded and has a local maximum at the round sphere. At the standard round sphere. So, okay, there are many open questions. There are certain things we don't know about the behavior of the determinant and the general setting with conical singularities. And so what we did in relation to this is a Polyakov Formula that I proved together with Klaus, Kirsten, and Rowlett. So it's the same setting. Yes, so we have this. We multiply the metric everywhere by a smooth function. So we have a surface with conical singularities. And then we have that H is 8250. Okay, I better write it with the H, because detail is not relevant now. So, and then we have this function is smooth everywhere. So it's smooth on this manifold. So it's smooth, like it could be extended through the boundary and smooth through the conical points. So if we have that, then we have the following formula. Log of the determinant delta H minus log delta G. And I don't see the time.
5 more minutes.
5 more minutes. So this is the same expression. I will not write it up. So it's the same expression as here. So this. Same as yeah. Plus one term. This comes with minus, there comes with minus. Here we have the sum from I equals 1 to M. M is the amount of conical singularities. Here. The function evaluated in phi I, we have a term from the angles. So this is the formula that we have. So we just have this additional term of H. And well, so this is our theorem. And then I should mention that also here, Dr. Calvin, he also proved a Polyakov formula, the same Polyakov formula for surfaces with conical singularities. So, also proof formula. So the same. or conical singularities, but he allows includes changes in the angle. So I didn't say this. So when I have a smooth conformal factor here, we should change this. Now, when I have a smooth conformal factor here, the smooth conformal factor so changes everything but doesn't change the angles. So the angles of the conical singularities are the same if I have such a transformation here. With a change in the angles, one needs to consider log functions that have I of r, like log of r, or something that we can see. And then that is included here in P2. So I have to say his word is more general. And so, but the methods of proof are very different. And our method starts with like the differentiation of the formula. So I could either give now in the last 4 minutes, I could give an idea of the proof of this, or I could give the formula for tons and spectros. What do you prefer? Or I just say quickly one and then I say the proof. Yeah, okay. So about the proof is really about the proof. So what one does is one considers a family of metrics of the form. So yeah, so one considers HU. This will be of the form e to the 5u g, and then 5u. So one can take just this a family of functions. So this is smooth in M, but also smooth in U. And to integrate the formula, so one can consider this general, but one can consider or later, we restrict the case 5u equals 0 plus h plus u plus u theta, another function. These are smooth functions. Right. So one considers this. One considers the Laplace operator associated to each of these functions. And one has to make sure that even though these are just conformal perturbations of the metric, one can carry out everything. So one can define the determinant, one can define the trace. The trace has an asymptotic expansion, one has everything. So one can have everything the same for this. So the point is that this is not difficult because many things are done already and then they fit well. So for example, we need also some estimates on heat kernels that are also well known. So like all the ingredients are there. So we can just take the spectral theta functions and we can differentiate them respect to u. So we take these derivatives respect to u of the spectral theta function of u. I just of S. And so we use the formula that I did already, but so okay, we just differentiate this respect to u. Right. So this is like the classical proof, follows without problems, because for example, when one has other settings, there are many problems and then one has to prove many things, but in this case, it's not. This minus yeah, we have here we have a number that I call it wrong, but I don't know how to call it. du, the dimension of the kernels of this. That's -1. Okay. Now I have to call it H, so that H will be H for this number and H for the other one. So this is dimension of the kernel. So we differentiate this, and then what we prove is that we finally prove, after making several computations that we can do, we prove that this derivative respect to u of the derivative of this respect to is equal 0. 0. At u equals 0. This is equal to h1 when this is the constant term of some asymptotic expansion of a heat trace that I'm going to write. So the trace in L2 of H0 of twice. This is the derivative respect to the parameter u. So this is in the parameter 2. See, and so I have this multiplication by this function, operator multiplication by this function. 0 naught. And then here I have e to the t 0 dash 0 minus the projection in the kernel. 0. So this trace has an asymptotic expansion that is exactly this one. 2 minus 1 plus a1 t 2 minus 1 half. And here we don't have log term, we have simply this term. And we have all the t1 half log of t. And then this is as t goes down to 0. So we just go through all this, and then we take that this variation is exactly this with this trace. So the following step is to use a parametrics to replace this heat kernel and to compute every term separately. Split into parts, and we use models, and then we can do that. So I think that's all what I can tell you today. Thanks for your attention.
Have that question.